Hey everyone, welcome back to Derive It, and we're going to be solving this problem here, climbing stairs. So this is a really good problem of dynamic programming when you're getting started, and I just want to remind you, dynamic programming is really easy. It's the same exact thing as recursion, so you solve this problem using recursion like you would any other problem. Except at the very end, all you have to do is add one little thing that makes it dynamic programming. Okay, so we're climbing a staircase, and it takes n steps to get to the top. And they say each time you can either climb 1 or 2 steps. So if we're standing here, we can either step 1 step or 2 steps. And same for every single stair. If we're standing here, we can step 1 step or 2 steps. And we're asked to find how many different ways can we get to the top. So for example, one way we could get to the top is just by stepping 1 step at a time like this. But we could also get there by stepping 1 step, 2 steps, 1 step, 2 step, 2 step, or 2, 2, 2, 2. There are a bunch of different ways we want to find the total number of them. So we want to find a function that computes the number of ways that we can get to the top step, step n. So that's really easy. Step 2 is where most of the work happens. So step 2 is to try and find a recursive equation for this problem. And we don't know that that's possible yet, but recursion is the easiest way to solve any problem, because if we can find a recursive equation, then we pretty much immediately have the solution. So all a recursion is it's when you have what you're looking for on both sides of an equation. So you have num ways on the left, and you have num ways on the right. So we're looking for a way to write num ways of n using num ways. And so now the question is, how do we do that? So num ways of n is the number of ways to get to this stair. The only ways we can get to that stair are by standing here and stepping there, or by standing here and stepping there. Those are the only ways we can possibly get to this stair. So this is stair n-1, this is stair n-2. So we either got here by stepping here first, or by stepping here first. All we have to do is say, what's the number of ways we could have gotten to this stair, plus the number of ways we could have gotten to this stair. That's the total number of ways we could have gotten to this stair. So we just came up with our recursion just by thinking really locally about the problem. The number of ways to get to stair n, which is this, is equal to the number of ways to get to stair n-1, plus the number of ways to get to stair n-2. That's literally what it's equal to. So this is our recursion, and it's literally just an equation. It just says the same way 1 plus 1 equals 2, this thing equals this thing. And the reason people care so much about these little recursive equations is that you can just apply them over and over again. Like you can just tell the computer, if you're looking for num ways of 5, you can apply this recursion and say the num ways of 5 is equal to num ways of 4 plus num ways of 3. Just applying this recursion. And then you can use that to break down these problems. The num ways of 4 is equal to num ways of 3 plus num ways of 2. And you can just keep breaking the problem down. So that's why people care so much about recursion. This recursive equation solves literally the whole problem, and it's really easy to come up with it. You saw how easy that was. So if you've seen the Fibonacci numbers before, this looks a lot like the Fibonacci numbers, and it turns out num ways of n is literally the nth Fibonacci number. So, theoretically you could just solve this problem as if you're finding the Fibonacci numbers. But let's just continue on. Let's pretend we don't know about that. And not only is it good practice for, every single other problem, but I also just want to show you that we'll eventually get the optimal solution that you would have coded up for Fibonacci just by following recursion and then dynamic programming. All right, so we have our recursion, and we know the recursion keeps breaking the problem down into smaller and smaller ends. So we're eventually going to reach stair number 1. And when we try using this recursion on stair number 1, it's going to tell us num ways of getting to stair 1 is equal to num ways of getting to stair 0 plus num ways of getting to stair -1. So this doesn't make any sense because it's talking about stair -1 and stair minus 1 doesn't exist. So this recursion, these two things are equal until you reach a certain point. Once you get to stair 1, the recursion no longer holds. This is no longer valid, and so you need to find what does numways of 1 actually equal if you can't find it using this recursion. Well, the numways of getting to step 1 is just 1, right? You start here and you can just step there. That's the only way to get to step 1. So numways of 1 is just equal to 1. And we can't use the recursion to find numways of 0 either, because that also calls negative things. And so what's the number of ways to get to step 0? Well, that's also just 1, right? We start at step 0, so there's only one way to get there. You start there. So now we have our recursion, and we have our base case, and believe it or not, that's everything we need to write the full solution. So let's just code that up really quickly. Okay, so the way we would code this up is we would just say we would define a function numways that returns whatever numways of n is equal to. So normally it returns the recursion, which is numways of n minus 1 plus numways of n minus 2. Normally numways of n is equal to this. The only time it's not equal to this is if we're in the base case. So if n is equal to 0 or n is equal to 1, then the number of ways is just equal to 1. So we're just going to return 1. And we want to call that on the n we're given. So we want to return numways of n. And so that's the full code, and that'll work. The only thing is, if we actually submit this, it'll take too long to run and LeetCode won't accept it. So why is it so slow? So when we call our function on something, like when we call numways of 6, that's going to call numways of 5 and numways of 4. And numways of 5 is going to call numways of 4 and 3. And I didn't draw the full tree, but you can kind of see here that there are a lot of the same computations happening. Like numways of 4 gets called here, and it also gets called here. Everything that gets run here is going to be exactly the same. So we're duplicating a ton of computations. So to speed up our code, we want to make it so that it doesn't do the same calls multiple times. And for some reason, people gave that a fancy name. It's called dynamic programming. So let's just do dynamic programming. It's really simple. So notice that numways of n only depends on the previous two numways. And so what that means is if we want to compute numways of 6, for example, then first we need to compute numways of 5 and numways of 4. And the same for these guys. If you want to compute numways of 5, first you have to compute numways of 4 and numways of 3. All the way down to, the base case, which is numways of 1 and 0. So numways of any of these things depends on numways of the things below it. And so we can just start at the very bottom here and compute things bottom up. So first we're going to compute numways of 0 and 1, and that's easy, we already know them. And then now that we've computed them, we can compute numways of 2, right? Numways of 2 depends on these, and we've computed them. And now we can compute numways of 3. And 4 and 5 and 6, and now we're done, So we're still using the recursion in the base case to compute everything. We just did it in a for loop, and that lets us easily avoid redoing the same computations multiple times. So let's just code this up. So we need to store all the values of numways that we've computed so far, and I'm just going to do that in an array. So the numways of index I here is going to be equal to numways of I that we've computed. And so that's going to start out as numways of 0 equals 1 and numways of 1 equals 1. And then we're just going to compute, numways of 2, 3, all the way up to n, like we just talked about. So this has to start out with the base case here. So first of all, this is n plus 1 items, right? If we count 0 all the way up to n, that's n plus 1 things. So this array is going to have n plus 1 items in it. And we need to start it out with this base case here. The easiest way to do that is just put every element to be a 1. So this just starts the base case out right. And then we're just going to iterate. We're going to say for I in range, 2 through n. And we need this plus 1 because Python is exclusive. And then we're just going to apply the recursion over and over again. And then when we're done applying the recursion, we're just going to return numways of n. That's the thing we were looking for. Alright, so I tested this and it works. So what's the time and space complexity of this thing? Well, we're storing an O of n sized array. So the space complexity is O of n. And then we're doing a loop over n items, so that's O of n time. So this is the complexity of this algorithm, and we can actually do slightly better. We can get rid of this O of n space. So notice that each numways of n only depends on the previous 2 numways. So there's actually not a reason that we have to store this whole thing. We don't actually have to store every single numways of n. We really only have to store the previous 2. So we're just going to start out with numways of 0 and numways of 1. And then we're going to compute this, and once we compute this, we don't have to keep remembering the 0 anymore. We can just forget about it. And then after that, we can compute this, and then we don't have to remember numways of 1 anymore. So we really only need to store 2 things at a time as we iterate upward. We don't have to store all of them. So we're going to need variable names for these things. I'm just going to call this prev and this cur. So we can just take our old code, and this is going to become cur, and this is going to become prev. And instead of storing this array, we're just going to store, prev and cur. So prev, this is going to be numways of 0 at the start, and cur is going to be numways of 1 at the start. And, those are both just 1. That's our base case. And then after that, we're just going to iterate the same way as we did before. So now cur is going to become the sum of these 2 things, and prev is going to become cur. That's just, how you update the pointers. And then we're just going to return at the very end, and I tested this and this works. So the time complexity of this code is still O of n. But the space complexity is now O of 1. And just notice that this code is probably the code you would have come up with if you knew these were the Fibonacci numbers and you just wanted to quickly code this up. But we got it just using recursion and dynamic programming, and that always works for any problem. So in this video I showed you how to solve any dynamic programming problem using a method called tabulation. That's just what it's called. And it's always optimal, which is why I showed it to you. There's one other way you can do dynamic programming called memoization, but often it's not optimal, and so there's not really a point in using it when you could just do tabulation. So at this point, you literally have everything you need to solve any recursion problem and any dynamic programming problem. So we're just going to do a bunch of practice next, and I'll see you in the next video.